horizontal table, and this is a massless table, which means we don't need to worry about it. It can't stretch. This will be important when we look at tension. We'll start off, as we do with any force diagram, or any force problem, with drawing free body diagrams. This time, because we have two masses, we'll need two free body diagrams. My first free body diagram will be for M1. My second free body diagram will be for M2. M1 has a number of forces acting on it, 3 to be specific. We have gravity acting downward. I'll call that Fg1, since it's the force of gravity on M1. It's on a surface, so it has normal force acting on it. And it also has the force of tension acting on it. M2 has two forces only acting on it. Tension acts upward, and the force of gravity on 2 acts downward. Now, because we have a massless string that cannot stretch, these two tensions are equal in magnitude, although obviously not in the same direction. Now that we have drawn free body diagrams, we can write net force equations. We're going to write a total of 3 net force equations. We may not use them all, but it's always a good idea to write them, because you may need them later. For M1, I'll write the net force in the x direction on M1, and tension happens to be our only force in that direction. That equals M1 times A. Looking at M1, you can tell right off the bat, M1 does not accelerate in the y direction, only in the x direction. So when I write my net force equation in the y direction, which includes the normal force and the force of gravity, I'm going to set those two added together to be equal to 0, because the acceleration in the y direction is 0. That means that the normal force is equal in magnitude and opposite in direction to the force of gravity. Looking at M2, notice there's only one direction of those forces on M2, only in the y direction. So I'll just write net force is equal to tension plus Fg2, and that equals M2A. Now, these objects will move as a system. That means that they have the exact same acceleration. So the acceleration of object 1, M1, is the same as the acceleration of M2. That is key to solving this problem. Looking at what we're looking to find, it says to find the acceleration of each object and the tension. We'll focus on the acceleration first. If you think about this problem, we're going to consider it to be a system. There's two masses in our system, as well as a string. M1, M2, and the string. We know that the net external force on the system is equal to the mass of the total system times the acceleration of the total system. I'm going to write that separate down here. The net force on the system equals the mass of the system times the acceleration of the system. That's the net external force. Well, looking at all of these forces here, the forces we have on our free body diagram, tension is a part of the system, because our system is the two masses plus the string. The normal force doesn't cause an acceleration, so gravity is the only external force. Specifically, the force of gravity on block 2 is the thing that causes our system to move. So when we say the net force on the system, we're really saying Fg2 is equal to the mass of the system times the acceleration of the system. The acceleration of the system is the acceleration of the two blocks. So if I want to find the acceleration of these two blocks, I divide Fg2 by the mass of the system. And the mass of the system is M1 plus m2. Remember we learned in class there's a specific equation for the force of gravity. That specific equation is mass times the gravitational acceleration. The other thing that I'm going to do is I'm going to stop worrying about vectors. I'm just going to solve for the acceleration, the magnitude of the acceleration of the system. Since I'm not worrying about vectors, I'm not going to plug in a negative sign for g. m2 is 10 kilograms and m1 is 5 kilograms. So I have 10 kilograms times 9.8 meters per second squared divided by 15 kilograms. Okay. I can plug those numbers into my calculator, and I get 6.53 meters per second squared. That's the magnitude of the acceleration for our two blocks. m1 accelerates to the right, m2 accelerates downward. If I had not ignored the vector symbols, this would just end up being a negative number, and I'd have to look at my scenario to understand what the direction really is. So that was half the battle. We found the acceleration of each object. Now we have to find tension. Tension appears in two different equations, and it's up to me as to which one I want to use. But this equation here is clearly the easiest one to use. That equation tells me that tension is equal to m1, which is 5 kilograms, times the acceleration we just solved for, 6.53 meters per second squared. This gives us a tension of 32.67 newtons. When a problem is asking for tension, you do not need to worry about direction, because as you can see, as I mentioned before, the direction of that tension does change. So again, when you have a system that is moving, you can say the net force on the system, and that's the net external force, so no forces within the system count here, equals the mass of your system times the acceleration of your system. The net external force was the force of gravity on m2, because that's the only force that's not within the system that is causing the acceleration. Fg1 technically isn't within our system, but it doesn't cause an acceleration. Same thing with normal force. Fg2 is our only force that causes an acceleration of the whole system that is an external force. So I used that to calculate acceleration, and then I went back up to my net force equations and used the easiest one to find tension.